Okay. Yeah, we can actually mute it somehow. I don't know why. Okay, good. Thank you for reminding. So people can hear. So for the electric voltage levels, initially we said if VGS less than VT, yeah, yeah.
The source that the arrow demonstrates the source.
Again.
The arrow from the node is that demonstrating that it's the source and not the drain?
From yeah, well, no, the current comes from drain to source, so current continues to flow. Yeah. Arrow is always on the south side. For PMOS, the arrow moves to the top, but it's still on the south side. Yeah, arrow is always on the south side. Yeah, correct. All right. So, but if VG is larger than VT, we have a current, but how much current flow is going to decide. Remember this curve like this, and we have this one, and here we call it saturation region, and here we call a tried region. So what determines that? And this is the current ID, and this is the voltage VDS. So that's determined by VDS. So if VDS is larger than VOV, or if VDS is less than VOV, so there are two conditions, and VOV is defined as overall drive voltage, which is VGS minus VT. It simply says how much is VGS over VT, because VGS equal to VT is a point where you either have current or no current. But based on how much VGS is, and you can have either in tried mode or you can in saturation mode. So this diagram shows that, which means over here, the bottom is the source. And if you have a certain voltage, VGS, if VGS is larger than VOV, I mean, if VGS is larger than VT, you have current. But how much more is plus VOV? So this is the VOV. So you see, it's just this figure does not have actually any physical meaning. It's just like using it as an illustration, saying, well, how much voltage do you have to apply in order to have current? Well, you have to apply, first of all, VGS has to be larger. VT, how much larger? That's the VOV, right? So this VOV determines if VOV is this much, but then you have VDS, if VDS much more than VOV, trial. If VDS larger than VOV, you have the saturation region. So that region, we call this, if VDS is less than VOV, we call this a tried region. If VGS is larger than, no, this is. So just kind of understand the voltage. Your voltage increase, VGS increase. There's VGS on this side and VDS on this side. Your VGS too low, no current. You increase VGS, you start to have current. But how much current determines on VDS? If VDS is too small, the current is small, and VDS is bigger, the current is bigger. So that's the relation. And eventually, we summarize everything in a table. And this table, you copy of it. Because this one really illustrates what is the relation between VGS, VDS, and basically, we divide this into two regions. So in this region, we call it trial. Trial region means VGD larger than VTN. Well, why is that way? Because that's what happens if you look at the diagram over there. So if the VDS, because source is grounded. The source is grounded. So here, from here to here, you have VDS. And from here to here, you have VGS, right? So apparently, so VD, and from here to here is VGD. So you can see here is VDS equal to VGS minus VGD. Or in that sense, is VDG. If you flip that to VDG, is VGS plus VDG, right? Because that voltage on this side or this side, they're the same from top to ground. So by doing that, you'll find it because VGS has to be larger than okay, we can probably just forget about that, and then we can just go on to discuss it. So once you have this one, the VDS less than VOV, I'm going to try. And these two are basically equivalent based on that equation. If you plug in that equation over here, okay, here. But I remember this one is easier than this one. Now, why would you want this one? Because later on, we're going to say, how do you make an amplifier? And this is exactly what we're going to do, what we're going to use. We connect a gate to drain directly. Again, that's a little bit ahead of your context. But if we connect gate to drain, what happens is VGD 0. VGD 0. If VGD 0, which means it's always less than VTN. VT is the threshold voltage. N means MOS. So if VGD is always less than TN, is here. If VGD always less than VTN, because this is 0, this is not 0, therefore you're always in saturation. So you guarantee that device is in the saturation region. That's why this is important. But again, for now, just simply this. So if VDS less than VOV, means your VDS is too small. Even though VGS is already larger than VT, but your VDS is so small that it doesn't induce too much current. So therefore, it stays in the triode region. If it is in the triode region, this is the equation to calculate the current. You have VGS minus VT, this is VOV, and this is VDS minus 1/2 VDS. Or you can plug in this number here, you'll get this equation. These two equations are the same thing, okay? That's okay. But if VDS is larger than VOV, we move on to saturation region. In the saturation region, current has nothing to do with VDS. So once it reaches saturation region, you change VDS, it's no longer have an impact on the current. So therefore, you have this equation, which this is the VOV. So these two equations are the same. So you calculate VD based on how much is VOV, based on also, these are the property of the transistor and there's width and length of the transistor. So this are very important. That the top over there, it shows, but I can also draw a couple of like different diagrams. And you probably know what the other two red lines means. It means you have a different VGS. So if we change VGS, that curve is going to change. But regardless how you change, the left hand is your triode region, the right hand is your saturation region. And in this class, we are more interested in the saturation region. Oh, yeah. So we have curve for the bottom, GS less than VT. And when VGS is larger than VT, you have different curves. And when you vary VDS, like doesn't change in saturation region, it's in linear region. Sometimes we call it triode region. Here is but if VGS VOV, you have current. Now, because when VGS increases, your VOV is different, right? So that's why we have different curves. So this is we're gonna from here on, we're gonna look at so basically if you translate that, you get this curve. Basically, we plot ID as a function of VGS instead of VDS. You remember from the previous slide, what we had is we have ID as a function of VDS, right? But here you can translate, because this is a different VGS, you just You just plug in this one, you got this curve. Not too much to work on that one, but we want to get into sort of a equivalent circuit of the MOSFET. So the symbol for MOSFET in the saturation region, our current ID is equal to 1/2 kW L VOV squared. So this is the current, and this current is only determined by VOV, which means for any MOSFET, if we are given VOV, our ID is going to be constant in the saturation region. So that means if we, now let me write down also what VOV is, VGS minus VTN, and again, that is indicator MOS. So think about it. If you are given certain VGS, your output current is fixed, has nothing to do with VDS. But if I change VGS, because VT is given, right, for any device, once it's manufactured, it's a fixed volume. If I change VGS, my current is going to change. So there's a relation between my ID and VGS. In other words, all VGS is controlling how much current you have in the device. What would you call that relation? I heard somebody saying control. It's a controlled current source. It is a controlled current source. So ID is, so when VGS is fixed, ID is constant. So it's like current source. But when VGS changes, ID change. So that is a it's not a linear relationship, by the way, because there's a square over there. So ID is a controlled source that is controlled by VGS. So how do you express a controlled source? In circuit theory, we use this as a controlled current source. And that current source is expression. And in this expression, we do have VGS, that is a controller. Therefore, we have VGS coming in somewhere. And then we have this current, which is related to VGS current source. So that is your, it's not a small signal model. It's actually, we call it a large signal model. It's just the equivalent circuit of your MOSFET. So, but I want to ask you too, which means whatever you connect the VG, what happens to the current? Like if I connect just a simple voltage source, would you have current flowing in that branch? No, because it's open circuit. Well, that explains exactly why we have a MOSFET. Yeah, if we have a voltage source and we have ground over here, we have ID. So if you look at this equivalence, I mean the actual MOSFET circuit, you have VG connect to the gate. Because the gate is insulated, there's no current. It's like open circuit. So that's why we have equivalent, well, we have VGS floating, because it connects to your gate, and the gate is floating. Like, I mean, theoretically, it's connected to the MOSFET like a capacitor, but when you don't think it's a transient, it's like open circuit. So VG is over there. So no current into the gate. Only VGS is controlling how much current at the drain to source. So we call this a controlled current source, and the current source is controlled by the gate voltage, right? Large signal equivalent circuit. So here up, there's just a bunch of numbers, so probably difficult to get all the actual result. But the idea is that if you are given all the parameters. 0.18 micrometer process, L is 0.18, W is 2, process technology specified COX and mu n and so on. Okay? And then VT is 0.5. They want you to find VGS that result in the MOSFET operating in the edge of saturation. And ID is 100 micrograms. How do you approach this problem? Well, what we're doing is at the edge, we can write ID is equal to 1/2 K, which is mu COX. And then you have W over L, and then you have VGS minus VT squared. That's at the edge. Because at the edge, you can either use the trial equation or you use the saturation equation. They're going to merge on the same place, right? So this equation is simpler, so we use this one. Now, mu is given, COX is given, WOL is given, and ID is given, 100 micro. So you plug all those in, VT is given. So you would simply go plug all the numbers in, you should be able to get VGS. The only thing you have to be careful is when you take a square root of both sides, you get plus and plus and minus on the other side, right? So then you would have 2 VGS. So sometimes you have to verify VGS is the correct value. Now, sometimes VGS gives you negative, which you know is not right, but sometimes it gives you 1 volt and 3 volts. What do you do? Well, you have to go back, verify. It's actually larger than VT. If VGS is larger than VT, yeah, correct. If VGS is less, correct, right? So you have just to be very careful about that. And then the next question is that if we keep VGS constant and find VDS that result in 50 micro. Well, if ID is 50 micro and saturation current is at 100 micro, so probably this is in trial. So you go use the equation and you solve for VDS. So this means if ID equal to mu COX, mu W over L is VGS minus VT, VDS minus 1/2 VDS squared. And from here, you can solve for VDS. Similarly, because this is a quadratic equation, you will have 2 values for VDS. I'm not going to write down. So, but you know that VDS is going to have 2 values. Only 1 value is going to work for you. So that's the idea. I don't want to go to actual number. You guys can do it on your own. But just towards the end, you'll get 2 values. One of them is going to be a good solution, but the other one actually is not right. So you have to go, how do you verify? There are a couple of things, right? So one is that your VGS has to be larger than VT. That's the one that, first question A. And then you have VDS has to be larger than VOV or less than VOV. Now, if VGS, right, if VGS larger than VOV, it goes to saturation, which means the equation that we use here is not right. So VGS has to be less than VOV in order to try the region. Those are the things you could go back to verify those two solutions. Okay, so that's important. Sometimes students started to get solutions and so on. So what happens? Okay, so there's another example saying NMOS transistor is operating at edge of saturation with a overdrive VOV and drain current ID. So if VOV is doubled, and we must maintain operation at the edge, what should be VDS changed to? Well, similarly, because it's at the edge, so we can do the equation like ID equal to 1/2. So this is the equation for saturation. So at the edge, you started just to have this. And we know that VDS is equal to VOV. So that's the condition for this thing to stay at the edge. And over here, you have VOV equal to VGS minus VT. So all those things you can write up. So the equation says that if VOA is double. If VOA is double, what should VDS be designed to so that your system will maintain still at the edge? So because VDS has to be same as VOA in order to be in the edge, if VOA double means your VDS double. Yeah, exactly. So VDS double, so that's the equation solution over here. And how much current do you have if VOA doubles at the edge? Because when you double, look at the equation. If VOA doubles 2 VOA means squared means 4 VOA. So that's why you got 4 ID. Okay, so those are the solutions, very simple. Next example says VOA 0.5 linear RDS, VDS very small. What is the value of device transconductance parameter Kn? Well, yeah, so this equation is basically just back and forth asking you to use those equations. So for this one, VDS, when they say VDS is small, do you know what they mean? Means in trial. So they don't say trial, they just say VDS is small, so which means it's in trial. So VDS trial, and you have RDS is 1K, so which means, so RDS equal to VDS divided by ID. So, and then if you know your VDS, you can find ID, and if you know ID, you can find VDS. So what they're saying in the trial mode, basically you're going to have equation saying ID equal to KWOL times VGS minus VT times VDS minus 1/2 VDS squared. You're going to use equation like this. Now, if RDS is given, which means you can find that ID equal to VDS over RD. So you can find the ID by this equation. Then you will plug in this equation back to here. You see, on this side you have VDS, with ID with that equation over there, you got ID, right? And then, so if we plug in all these numbers over here to find, well, this one, KWOL is what they call this K. So Kn equal to Kn prime WOL. So that's the number that you need to find out. So basically, what we're saying is ID equal to Kn times all these numbers over here. So from here, you can find Kn. No. Let me erase this prime over here. So that's what we have in terms of finding Kn. Now, of course, in here, they want to ask you if VDS is increased to 0.2, how much is VD? And how about 0.5? How about 1? So you can use this equation to get it's in trial to get all the currents, but you have to verify. If it's not correct, you will switch over to that saturation equation so that you can get the correct value. The trick is that for MOSFET, because there's a square here, or either in one, the other one in the saturation region, you also have a square, VOA square, right? So that square makes our problem much more complex because you always get like 2 solutions, and then only one solution is correct. Solution is wrong. So that's the difficult part. When we get to BJT, we're not going to have this type of issues. Okay. So, okay. Right. Okay. So now we're going to move on to the what we call the finite resistance. Sometimes this is called pinch off. So what happens is that if you have a transistor, I want to draw the original drawing. So the original drawing is like this. We have a channel, oops, like this. Remember what we called about the channel effect? Well, all the electronics try to flow so that you get one side is bigger, you get trapezoidal, other side is smaller. So that's where our equivalent current is actually smaller than it's wide open. So we took the middle, right? So that's how we got the saturation region. And the linear, the triode region. In the saturation region, it's different. Now, sometimes if you further increase VDS, you got this channel. Side is open, but on the side it's zero, like a triangle. And you increase VDS further, actually move that away from the edge, the top graph. So the channel is no longer like a rectangle. The channel look at a triangle, not only just a triangle, but actually the other side of the triangle is not on the edge anymore. It moves towards the inside of the MOSFET. And it's called the drain. Effect is reflected by we're calculating. So now let me go back. So in the saturation region, remember what we said is ID has nothing to do with VDS. That assumption is only made that your channel is fixed. But if you increase too much VDS, the channel is no longer fixed, but it becomes pinched. It's pinched to a triangle and moves to this end. So naturally, your current difference is reflected by this diagram over here. So instead of a flat line, actually the current is going to be bigger, like this. So you increase VDS, the current ID is going to increase. Line to the second quadrant. For all the, and at the point, we call it, it's like what we call early effect. So this point over here, and because of horizontal X is voltage, so that cross point is corresponding to a certain voltage. And that voltage, we call it early voltage. So VA, or VA. But if we take the reverse of VA, we get lambda. We get lambda. And that lambda magically is related to how much the channel is pinched off. So you can actually observe this phenomena. Let's microscope, you'll get observe effect of this pinch effect. So that once that happens, our current is no longer now without pinching, our current equal to 1/2 Kn prime WOL VGS minus VT squared. So that's without pinching. With pinching, that current actually increases. How much increase? It's proportional to two things. One is the lambda, the other one is VDS. So if you change this lambda to be 1/VA, so it becomes VDS over VA. So that equation can also be written as ID equal to with pinch Kn prime WOL times VGS minus VT squared 1 plus VDS over VA. So apparently you notice that VDS over VA, because both have the unit of voltage, volts, so the ratio is unit less, and plus 1 gives you how much increase of current. This over here is a unit of current. So which means if there's a pinch effect, my current is going to be more. How much more? Determining on VDS and VA. So VDS is small, and this number will be small, you can be neglected. Your VDS, the big VA is small, and this cannot be neglected. VA is typically in the range of 5 volts, 10 volts, or maybe 30 volts, and depending on the channel length of the device and the material. And VDS, of course, is something that we apply. So VA is a fixed number for any given device. But VDS is something we can change. So this is called pinch effect, or sometimes early effect, early voltage. Now, remember the equivalent circuit we had before. I want to just again this is the MOSFET, gate, drain, source, and we have the equivalent circuit. And then we have this current to be 1/2 K WL, and let's try to VOV squared. So G and S. Right. So that's what we have for the initial equivalent circuit. So now you have a pinch effect. So in theory, if you just put this number, extended the equation, you would have like equivalent circuit. But it turned out that because this has a VDS is a variable, so we kind of don't want the VDS to be there because it's a control voltage source related to this one, but you get another variable, so it's really not nice. So we want to do something. So what would you do? Well, from this equation over here, you guys know what this is about, right? The front part. This part is actually the current without pinching effect. So I can write that as ID times 1 plus VDS over VA. And I put ID inside. I can do this. So I simply put this as ID and multiply this inside. I got ID plus ID over VA, VDS. Now you see VDS is what? So VDS is the voltage from here to here on the graph over here. You have VDS. But, so this is VDS. What, like this one, ID over VL is, what is that? Or you flip that, what do you get? You get a resistance, right? So it's a conductance, but also a reverse of resistance. So basically, I can write this equation to be ID equal to ID plus VDS over R. And then that we call this RO. And this RO equal to VA over ID. So once your transistor is designed, VA is a given number, and ID often is given. Basically, I mean, when VGS is given, your ID is given. So when ID is given, VA is given, this actually is a constant, which means O is a constant as long as the ID is fixed. But if ID, of course, is changing, I will change. And then you have VA over ID, which gives you resistance, and VDS is there. What can you do now? Well, we just simply, instead of that equation, we can write, well, it's already here, so I don't have to draw it. So the initial current is ID plus R, and RO is VDS, which is divided by is the current over here. So now you have really a control source by which, and then you have RO is the pinch effect or the early voltage that is related to the channel pinching effect. So this is the equivalent circuit, and RO is a number. So we can write down here. So RO equal to VA over ID, right? And then your ID equal to basically ID plus VDS over ID. And this can be, ID can be written as 1/2 K N prime WL VGS minus VT squared. So that's all the equations that you need. Now, again, we are all talking about is saturation region. And these equations does not apply, these equations do not apply to the triad region, okay? So now we can have an example. So this example, it tells you a bunch of stuff. COX is given, VA is given, L is given, W given, VA. They want you to find VA and lambda E. So how do you find the lambda? We just wrote the equation. Lambda is equal to 1 over VA, so you can find 1 over VA. Well, it's interesting. VA is given. Why would you find VA? I don't understand. Find the value of ID, the reactor when the device operated with the overdrive voltage of VOV equal 0.2 and VDS 0.8. So basically now you're going to plug in that equation equal to 1/2 K prime in this case, we'll simply use this equation here. We're simply going to use W what? WOL times VOV squared. So if VOV is given, K is given because K equal to the COX times mu. So that's the K. What else? LW are given. So you find ID. So yeah, so and then here you use this what is that? So ID over ID over VA times VDS. Right. So plugging on the numbers, you can find ID because you got only one variable to do that. So if VDS is increased by 1 volt, what is corresponding change ID? So you can basically start to find all the values that you want. So basically, without VDS, you got current. Now you have VDS increased by 1 volt. Plugging that in, you got the numbers. Okay. So that one you guys can do it. So today we're going to also cover 2.5 PMOS. Now, so far we have talked so much about MOS. We did mention about PMOS earlier. If you guys remember the physical structure for PMOS, this like MOS. Let me redraw those so you guys can have a better understanding. So MOS is the p-type material given N, and you have insulator, right? Then you have piece of metal here, and a piece of metal here. that's your gate, that's your drain, that's your source. And then that's NMOS. And then for PMOS, we have basically N type of material. You multiply this. That's how you build a PMOS. And then we also talk about CMOS, which is one NMOS on the side, you build a PMOS. So for PMOS, the equivalent circuit is PNP. So it's PNP. And so in the middle, you get P and like a P. The symbols similar to MOS, you got 3 different. One is the one. This one here has an arrow pointing to the direction of current. Like one student asked before, the arrow is always on the source side. So you can see arrow here now, that indicates the top is the source instead of bottom. For NMOS, the bottom is source, the top is drain. But here we flip it. So the arrow is from the source side and indicate the flow of current. Now B often is connected to source. So it disappears. So therefore, we got this one here. So you have source, drain, and gate. That's a PMOS. Current flows from source to drain instead of from drain to source. It's just because it's a PNP. So from P to N and then to P. So now for this one, apparently just by looking this one, you probably notice that if we have current flowing from top to bottom, voltage-wise, VGS has to be what kind of value here? Negative. Because VS has to be larger than VG. Because you're flowing current from top to bottom. So the top voltage has to be higher than the bottom voltage. So here, so in the future, we don't VGS anymore. We always use VSG in the PMOS. I mean, it's a little bit confusing, but it's think about the PMOS. So PMOS is every opposite to NMOS. Think about it. In the PMOS, our VGS has to be larger than VT, to conduct current. So here, what we say about SG, just if you were the one to, to be asked, what would you think? So VSG has to be large enough to have current, right? So that VSG has to be larger than VT. But unfortunately, the VTP is a negative number. Why? Because of p-type material. So from N to P, it's a negative, right? So VTP is negative. So, but then you say VSG has to be larger than VTP. It doesn't make any sense. So we will say this. We're going to use absolute value. Maybe in some other books, they use VPT, which means, okay, just get it a positive number. But in fact, if you look at PMOS, VT is a negative number. Now, in order to have VSG larger than this number, we have to use this absolute value. But once you do this, everything becomes very simple because this here. So VSG, well, we go less than VTP to have current. So basically, that's the number one condition. I can rewrite it just for you guys to review. So VSG less than VTP, there's going to be no current. That is exactly, I mean, I have a comparison between PMOS and NMOS. Maybe I can write down here so you guys would have a better understanding. So this is P, this is N. So for N, what you have is VGS has to be larger than VTN. I mean, not large. For zero current, it's actually less. Just write them to be consistent. Okay, so that's zero current. Now, if VSG and then ID is larger than zero, and here you have VGS is larger than VTN, right? So that's that's kind of the first condition that given was over here. But once VGS is larger than VT, or in this case, VSG is less than VTP, you have two choices. One is in the triode region, the other one is in the saturation region. So in the triode region, you have VSG, you have VSD. Now, why VSD? Why VSD? Because here we have DS. So from here to here is VSD, and from here to here is VSG. So everything is just flipped. Instead of VDS, we call VSD. So VSD has to be larger than, less than VOV, and then this VOV, we have to put absolute sign. And on this side, we have VDS is larger than VOV. So that's the triode region. And then in the saturation region, we have VSD is larger than VOV, and here is VDS is larger than VOV. And one of the current is exactly the same thing. So the equation is exactly the same. Simply replace K with KP, with KP. Everything is the same. Triode region and saturation region. So those equations, these are the same, these are the same. But what I'm saying is that for p-type, n-type, these equations are the same, except that you're going to use absolute value instead of, because this value itself is a negative. VOV is negative, so therefore you have to use absolute value. So given that, I think it will make your life is really easy by when you go to a MOSFET, think about replacing everything. Everything was flipped. So VGS becomes VSG, VDS becomes VSD, VTN, VTP becomes absolute value, and VOV becomes absolute value. And once you do that, the equations are exactly the same. And this diagram shows kind of illustration how you make the transistor conducting and how do you make it to work in the saturation region. So it's similar to for basically Vs has to be larger than Vg. VSG has to be not only larger, but it has to be larger than VTP absolute value in order to have current. But once you reach that point, VSD has to be larger than VOV in order to have the saturation region. If it's less than VOV, you will be staying in the triode region. So that's why on the top you see the right hand is VSD. So that the saturation region. So that's just the illustration. No physical meaning, just illustration. So here, let's see. So I want to just go back to, again, compare NMOS and PMOS. So we have a better. So for NMOS, our equivalent circuit is G, D, and S. For PMOS, and the conditions to have current is if VGS is less than VTN, ID is 0, or we call it off mode. And in this case, the VSG is less than VTP. That's the condition. So that's number one. And number two is VGS larger than VTN. This is on. And VSG is larger than VTP, and that's on mode. And from here, we have 2.1 is if VDS is less than VOV, this is in trial. And here we say if VDS is less than VOV. Okay. And then 2.2 is if VDS is larger than VOE, we have saturation region, and this is, oh, VSD, sorry. So again, so writing, I'm making a mistake. You guys hopefully don't make the same mistake. So this is VSD. VSD is larger than VOE. So that's two conditions. And the equations for the triode region and for the saturation region, for example, this ID is going to be, there's not enough space for me to write it, but we can write down here maybe. So for 2.1 is ID equal to AWOL times VGS minus VT. And for this one here, you have ID equal to KP, and the previous one is KN prime, so KP prime WOL times VSG minus VTP times VSD minus 1/2 VSD squared. So that's the difference. So for 2.1, so that's 2.1. Now for 2.2, we have ID equal to 1/2 KW over L times VGS minus VT squared. And here ID equal to 1/2 KP WOL VSG minus VTP squared. And here we didn't consider the pinch effect yet, but if we get the pinch effect for the saturation region, we will simply multiply this by 1 plus lambda times VDS, or like VDS divided by RO. So that's why we have equivalent circuit later on. So examples here, this is a video example. You guys can watch video in your digital textbook. But what this does is that they want to we are given the transistor, we have VTP is given, see here, it gives you minus 0.5. So basically, when you do this problem, just go ahead saying VTP equal to 0.5 volts. So forget about minus sign. Just simply use the absolute value. And then it says VG varies from 0 to 3. Now, you see here, so VSG, now this is S, this is G, right? So VSG is 3 minus VG. So that's important. So VSG is 3 volts is a power supply, minus VG 0. So when VG is 3, your VSG is 0. When VG is 0, SG is 3 volts. That means so your VSG changes from 0 to 3 volts. And within that range, you can imagine that your transistor from to triode to. So because your VTP is 0.5, at what region would you have off? So if your VSG is less than VTP, it's off, right? So from here, which means your 3 minus VG is less than 0.5, and that gives you VG is larger than 2.5 volts, right? So if VG is too high, SG is too small, not enough voltage to turn on the transistor, so you're in off rate. And then the second condition is, at what voltage would you have in the triode? Well, in this case, we have VDS. So VDS has to be larger than VOE, and then that VOE equal to VSG minus 0.5. Here is in the saturation region. Now, of course, you can flip that with the tried region will be VSG, VSD. Keep making mistakes here. Sorry about that. Oops. Good. Okay. Yeah. So VSD. So using this equation, you can simply find out at what VSG range your transistor will be either in saturation and cutoff. There's a voltage. Now, because the absolute value over here, so just be careful that which one that you use, because with absolute value you can get plus and minus. So that's something you have to be careful doing the calculation. Okay, so that's this equation, very simple. And then okay, so this example is a little bit long and complex, but I just want to go through the procedures. Now we're not going to plug in actual numbers, so you guys can do that. Conducts means it's not off, which means it could be either in triode or it could be in saturation. So in this case, what would you do? I mean, based on the previous example, you know that we need to find that VSG has to be larger than VTP. And VSG is equal to VS minus VG, which is equal to 1.8 minus VG. So from here, you can go in and find the range of VG. So the solution that VG has to be less than 1.3. If VG is too big, you're not going to work because VTP is 0.5. So 0.5 plus 1.3 is 1.8. Right? So that's what we get. And then B asks you to find VG, you find the VD for which the transistor opens the triode region. Well, in the triode region, what we're saying is our VDS has to be less than our VSD. VSD has to be less than VOV. Now, first of all, you want to find VOV, which is equal to VSG minus VT. So plugging that equation, you'll find VSD as a function of VSG. T is given. So from there, you can find out, well, VD has to be larger than VG plus 0.5 in order to be in the saturation region. Or actually, in the saturation region, I need to rewrite this one. Should be large. Yeah. So you find that B. Now for C, it asks you to, in terms of VG, find VD, consider operate. Oh, actually, sorry. It's in triode. It's in saturation. I read the wrong line. So. And then for C, of course, the VSD has to be larger than VOV. So those two equations are the same. You'll find the same boundary. I mean, just one is larger and another one is smaller. Your VDX increases, your VD increases, and your VD is here at the bottom. If the bottom of the transistor voltage is too much, there's no current. Now, I'll give you an extreme example. Your VD is 1.8, what happens? Yeah, voltage up and bottom the same. You'll never have current, right? So VDS has to be small. How small? That's those equations, okay? And then move on to D. it asks you to neglect the modulation of the pinch shift and find and corresponding VD operating transistor saturation with ID 50. So to do that equation, you basically, because you know this in saturation, so now you know that ID equal to 1/2 K WOL, this is Kp, and then here you have VOV square, and then of course VOV you know is VSG minus VT, right? So you got that, you plug in this number, ID is given, W is given, Kp is given, L is given, you should be able to find VGS. Okay, so we found VGS 0.328 volts, and all these numbers now you find. And that's D. And then going to E, it asks you what happens if you have lambda given. Well, for lambda given, we know that ID is going to be 1/2 Kp WOL VOV squared 1 plus lambda. Now here is VSD, okay? No square, just that. So here you plug in lambda, or you lambda is given. You find in D at VD is 1 plus. You see, when VD is 1 plus, which means VSD is 0.8. So you're basically given VSD, which in that equation, VSD is given, lambda is given, all the other numbers are given. So it's easy to just plug in and find the number, right? So that is, and also you calculate what is the current 0. So this, we would just plug in those numbers and we'll find the solutions. Okay, so this is actually step by step how to do those and so on. So you guys can do this later on. And also lastly, they want you to also find the value of IO, which is VDS OID, and gives you 100 kilo ohms. That's the small signal equivalent circuit. Let's see. I think what I'm going to do is we're going to leave, especially over next week. We're going to have some more examples. But as I said, on March 19th, which is the week before the final, we're going to have one dedicated lecture on just problem solving skills on MOSFET. And then on that Tuesday, you guys have another lecture on solving skills for BJT, and then you have your second middle term. So I'm going to skip some examples, and we're going to move on. So I'm going to stop here. Any questions? Okay, if not, then we're going to conclude. We're going to move on to the next section next week.